Thank you so much, and I'm sorry for the technical difficulties. I do thank you for your kind introduction. It's an honor to be invited to speak to the Endocrine Society of India and the International Society of Endocrinology, and I thank the program organizers for that. I did give a talk once down south in India, but have not had the pleasure of traveling extensively, which is going to be difficult now. So here we go. This is the University of Virginia. This is Mr. Jefferson's college. You see the rotunda in front of you, the academical village, which is right behind it. And then looking absolutely westward, you see onto the rest of our country. So that's the university where I am, and I've been for the last 46 years. So what are we going to talk about today? What we're going to talk about today is relative energy deficiency in sport, also called RED-S. I will use that more than once. It was formerly known as the female athlete triad. I'll go through exactly why in the first few slides. And it has to do with low energy availability with or without an eating disorder, low bone mineral density and stress fractures. That fits in with the lecture that we all have just heard. Functional hypothalamic amenorrhea. I will go through part of the mechanism of that. And now why we call it relative energy deficiency is because we now have males, and I will show you equal opportunity for the males. But most of the mechanistic studies have been done in females. And I do want to make a point here that we're going to talk about relative energy deficiency. And we say sport, but it's a lot of things other than sport. And I will go through some of those. The next one is why it's called the female athlete triad in the beginning. Because as you see in the green, if there's optimal energy availability, optimal bone health, and eumenorrhea, you don't have the condition. If you come to the full condition, you have low energy availability and often, but not exclusively, an eating disorder, osteoporosis, as was mentioned just a bit ago, and functional hypothalamic amenorrhea, which I am going to discuss in detail. Now, how you get from here, that is the green part, to the red part, tells us a little bit about its pathophysiology, but also it tells us what we might be able to do to prevent it. Now you see the red, the blue, and the green color. On this slide, it takes up exactly those things. So if you are if one is energy deficient, it can be fixed within days or weeks. In the outcomes, we'll see a little bit of the data. Energy status will stimulate the anabolic hormones and reverse energy conservation adaptations. We will see those directly. Then, for the ladies, obviously, recovery of menstrual status often will take months. The outcomes, the estradiol, the proj, because they're ovulating, and the LH will change. And remember from our last lecture that estrogen exerts an anti-resorptive effect on bone. Then we have recovery of the bone mineral density, again, just spoken about. It just takes longer. That's all. Get rid of some of the catabolic effects, add some of the anabolic effects. Okay, so I'm a pediatrician, and I believe very strongly in diseases or conditions through development. Here is the daily GnRH pulses during pubertal maturation. Why is it important? Because we're going to see that some of these pubertal processes are recapitulated as one goes from an energy deficient state to an energy replete state. These say GnRH pulses. Well, you don't measure GnRH pulses in humans because you can't get to where it is. What we measure is LH. And so what we see in these four panels is time across the horizontal axis and LH across on the vertical axis. Night is scheduled, day is scheduled. And you can see a relatively low amplitude not so regular pulse pattern in the prepubertal kids. As they go into early puberty, notice the difference between the nighttime and the daytime. At night, the pulses are there and they are larger, but only at night. As you go to the lower left, you see that, but you also start to see during the day pulses, yet there is still a difference between the higher levels at night and the lower levels during the day. And then as the adult, it seems like they're very regular pulses, but as we will see, physiology says or tells us that during sleep, the pulses slow down. So let's go to a real person. So this is LH in early puberty. She is, if you look in the upper left, a 10-year-old girl. 10 or 2 simply means that her breast development started a little bit ago and is really only a small amount but glandular tissue. Please note, however, LH now is on the vertical axis, time is on the horizontal axis, and sleep is listed above. Please note the lack of pulses during the day and the activity, but only at night. So let's move on in the pubertal maturation stage. And now we will go up to Tanner stage 5, which is essentially an adult with an adult breast. Notice now that the pulses are all day long, but the pulses at night are still a bit higher. And in fairness, they are spread out a bit more. But this is then the pattern of puberty. And let's see what happens to athletes. So the first slide about athletes is this one. This is a remarkably good experiment. Ann Laux did it and won an award that year for JCE&M, now some 17 years ago. So you will notice on the vertical axis, the energy intake and expenditure, kilocalories per kilo lean body mass. Why is that important? Well, it's important because that's the tissue that has metabolism. And so that's what you're worried about. And you will notice on the vertical axis in those bars, the controlled dietary energy intake, and you'll see along the horizontal axis what those are. So one would start at 45, and I'll show you data, and we'll march down, not in the same woman, but in different women in this experiment. Please note, we are talking now about an experiment of 5 days. That's all this experiment is, 5 days. So what we have here, upper right, we have a lady who has the usual amount of kilocalories per day, and it goes down to 30. If you look at those two patterns, except for a little bit of artistic license, they're essentially the same. Let's move to the middle. You will notice that this woman does have the nighttime increase in amplitude and decrease in frequency. If you now go down to the 20, that is the middle on the bottom, what you see is an exaggeration of that pattern. However, if we go all the way to the left, what do we have? We have what she was like at 45, but a very, very different pattern at 10, markedly under energy, energy deprived. But you will notice that there is a marked nighttime slowing as well as nighttime pulses. So that's what happens to the LH. Now, this is a little bit complicated, but I'll walk you through it. It's actually pretty simple. All the vertical axes are percent. So 0 is where you started. And that's why all of the lines in the right of each panel are at 0. And as you march down from the right side on the horizontal axis to the 0, you march down through those different amounts of calories that they got. So let's start with the upper left. And the upper left is beta hydroxybutyrate, metabolism of lipids. Glucose goes down. This is 2 times glucose just to get it on the graph. And you see that you use less carbohydrate and more fat. If you now go to the upper right, you see cortisol, which is one of the catabolic hormones, goes up, and insulin, one of the anabolic hormones, goes down. Start now in C, And what you see is growth hormone goes up and IGF-1 goes down in those people as they march down the calorie scale, and they are then growth hormone insensitive. This will come back to haunt us when we talk about male wrestlers, and leptin and T3 also go down. So these are the metabolic consequences of this kind of caloric deprivation. This one is starting to be a little bit more like me, the pediatrician, and now we are talking about adolescents. Here we have the incidence of amenorrhea in adults and adolescents who are athletes. You'll see what is called on the bottom gynecologic age. That's simply the number of years since menarche. So they could be of any age, but the anchor of this is their menarche. And what you see is it is much less in adults than in adolescents, or one could say the adolescent has a more sensitive hypothalamic pituitary axis. Now, this is again the metabolic effects. Notice the adolescents in the hatched bars, the adults in the open bars. And these things are pretty much the same in terms of amplitude in the middle, but please notice that on the left, the frequency goes down. And remember, on the right, the 24-hour mean is a product one way or another of the frequency and the amplitude. And so here, we're now looking at the metabolic consequences, and as opposed to what we saw just now, it is pretty much the same between the adolescents and the adults. The only thing that's different is the growth hormone levels. IGF-1 is a little bit different, but not enough to be statistically significant. So there is still a metabolic effect on growth hormone. And for those of us who are pediatricians, we talk about growth hormone, but if you're an adult using that hormone, it really is the metabolic hormone rather than growth hormone, because adults aren't growing. Yes, kids grow with growth hormone, but the metabolic effects are really also important. So this then is a single female athlete who started out before her training. On the left, you can see the calories per kilogram of fat-free mass, pre and post, not very much different, 7 kilocalories fat-free mass per day, but in her few months of training, there's a remarkable difference of the right side compared to the left side. I have been remiss in not talking about boys and men, so here we go. This is a compilation. This is not a single experiment. This is a compilation of case reports done by Matthias Grossman in Australia that show that at a baseline where athletes were energy deficient, both their testosterone above and their LH below are way below normal, but much more importantly, after weight gain, I'm not so sure because their case reports exactly what exercise did, but you can see that both the LH came back to normal, excuse me, and the FSH did as well. Now, this is an experiment that's going to take a little bit to define. This is U.S. Army Ranger training. These are not athletes. However, if you look at either A or B, and A or B are essentially the same, except in the Army, they took samples at the wrong time at B, and that's why this slide will look a little different. Please note that it is the estimated caloric intake in kilocalories per day in A. So the first part of it, they are replete, then they're out in the swamps or wherever else they're doing their energy training. Very hard work. You can't carry your food. You got to kind of get what you can, and you can see 2 or 3 separate times that they are doing this kind of training. And what you see on the bottom is the exact same thing, except the order is a little different. That's what the problem is. I'll try to explain it a little bit better on the next slide. So what we're looking at now is LH. And each time the LH levels were taken, they were at the end of the hard work time before they were refed to go out to the field again. The upper level is B because they took the samples at the wrong time. And what you can see is, of course, they have recovered. So this is LH. So they are hypogonadotropic. This is now their testosterone levels. And what is in the gray area here is abnormal. And that's pretty much what you just saw for the LH. Now, what does it mean? It means induced hypogonadotropic, hypogonadism. And because they made the mistake, you can see they recover really quite rapidly from this kind of training. The last group I will talk about is the adolescent wrestlers. This is my sport. So they compete in weight classes and weigh in before each competition to certify their body weight is within that of a particular weight class. They work out 800 calories. These are high school kids. This isn't what would happen in a college. It would probably be half again is more. And they may have nutrient intakes 50% below those recommended. Remember, these are growing kids. So to get along, you need X amount of calories. To grow, you probably need X plus 20 or 30%. So I will show you some particular data. They are evaluated 3 times, early in training, but they know they're going to go into training, and so they do bad things with their food beforehand, and I'll show you precisely that. Late in the season at tournament time, virtually all of us lost weight or tried to lose weight to get 1 class below, but everybody else is doing the same thing, so it really didn't make much difference. And then postseason is when you can eat what you want to eat and you're not exercising quite so much. So what do the data show? The evaluations are nutrient intake, anthropometrics, body comp, and just a couple of the hormonal axes. I'll show you those and then we'll quit. So nutrient intake, all of these slides are set up the same. On the horizontal axis, you will notice early, late, and post. And the circles are those boys who are the wrestlers. The filled circles are those controls of about the same age. Remember, these are teenagers who are growing. So already at the beginning of the season, their energy intake is relatively low. Late in the season, it's the same or less. And if you look at the 3 major nutrients, fat on the upper right, protein on the lower left, carbohydrate on the lower right, they all look the same. They are deficient in all of these macronutrients. What about body composition? So we'll go to body weight in the upper left. The filled circles show what you would expect. Kids of this age over an 8 or 9 month period ought to be gaining weight. So the body weight, remember some of the wrestlers are heavyweights. The body weight goes down between early and late and then pops back up. And if you look at fat, the fat mass, absolute in the upper right, the percent fat in the lower left, they both have a big decrease, and what they do is they jump way back up after the season is over. And the fat-free mass, which is the lower right, changes a bit less because their calories they've been using have come from fat. This is the IGF axis. This should not at all surprise anybody. We'll just look at the upper figures. You can see in A, growth hormone goes in the upper left, growth hormone goes up. IGF-1 on the upper right goes down a little bit, opening up the loop like we saw before, and thus someone is growth hormone insensitive or growth hormone resistant. One of the metabolic pathways that occurs when IGF-1, which is not only growth hormone dependent, but much more importantly, nutrition dependent. So what have I done? The growth in these adolescent wrestlers, the growth of fat-free mass and other soft tissues is slowed during the sports season, followed by catch-up growth postseason. The incremental growth, I didn't show you the data in stature and rate of skeletal maturation, didn't show you those data, is similar to that of controls during both the sports season and postseason. So what we're talking about is, in this case, the growth hormone insensitivity is what is important, but it's not important enough to keep them from growing. So let me conclude. Profound hypogonadotropic hypogonadism is associated with energy depletion in adolescents and young, otherwise healthy athletes. This condition is renamed the relative energy deficit in sport, rather than the female athlete triad. It should be pretty obvious because there are guys in there. So there are both women and men. It occurs not only in sport, as we may define it, but also any repetitive activity, the Rangers, the Army Rangers that we talked about, in which much or more, but in most cases, much more energy is expended than accrued from the diet. May occur in days in women, may occur in a few weeks in men. The men that were looked at were only at one time post their field training, and it may have been earlier that one could have seen these metabolic defects. Thank you so very much for your attention. I believe you are mute.